Hello, everyone. So we will continue our discussion about image processing from the last, which we were discussing from the last three classes. In the last class, we were discussing about how can we stretch a histogram. So we discussed about what a histogram means. For example, you can think of it as a progress report of your image, where you would know each intensity, how many pixels are there with that particular intensity, and what range of intensities are there. Let's say you have got a histogram, something like this for an image. Okay. And assume that 0 to L minus 1 are your range of intensities. First thing we wanted to do was called as contrast stretching, or you may call it as histogram stretching also. Essentially, the same thing gets reflected in the histogram also. So you may call it as histogram stretching. What is it that we wanted? Let's call this as F min, let's say, the minimum non-zero intensity value that you could observe in a given image. And let us call this as F max. Okay. And let that intensity be f of xy, which for simplicity, we will simply drop the xy indices. We simply call it as f. Okay. Now what we wanted to do, so that g, the new value of xy, again, I will call this g of x comma y also with the, for simplicity, I'm just dropping the indices value. So let me call this as g. This g is equal to, now what is it that I wanted is, I want this minimum to be 0, this maximum to move to L minus 1, and in between, it should linearly pick some other values. Okay. So can any of you tell me how can I achieve this? That linear equation, can you tell me?
F minus F min by F max minus F min into L minus 1.
Right, good. F max minus F min, this whole thing multiplied with L minus 1. Let us, good. Let us pay attention to what this one is doing. For example, I wanted this F min to go to 0, that value. So somewhere in your F, for some values of x comma y, the least value you could get for varying values of x comma y is F min. You want to that in your histogram to go to 0. So what has been done there? F minus F min. Okay. Now you want to first normalize these values to 0, 1 range. Okay. You are going to normalize it to the range of 0 and 1. Notice that from F, when you are subtracting F min, of course, F max also gets subtracted by this F min. And now your range of values after this would be 0, comma, initially the values are in the range F min, comma, F max. Right. You have subtracted from all these values F min. So this turned out to be 0, comma, F max minus F min. Okay. Now I want to normalize this to 1 in the first place. So how can I do that? I simply,
Sir, excuse me, sir.
yes,
In
yes.
the formula you written G equal to F minus F min. So
Correct.
F min I know from the
Ah,
histogram plot.
right.
F max also I know. L
Hmm.
minus 1 also I know.
Hmm.
What is F, sir? F means from each pixel we are intensity value of your mind.
Right. Correct. So if that is in doubt, let me write it as g of x comma y equal to f of x comma y, a 2D array I'm writing. Minus f min, f max minus f min into L minus 1. I will do this for every
Understood.
pixel.
Understood.
Is
Sir,
that
understood.
clear? Good.
Yes, sir.
Uh, yeah, good. So once I do f minus f min divided by f max minus f min, what is the range I am getting now? Initially with subtraction, I got 0 to f max minus f min, my range. Now I divided with f max minus f min. So what is the range now?
0 to 1.
Correct. The maximum value itself will be 1. Now notice the maximum value I want it to go to L minus 1. So these are value 0 will obviously be there at 0 with whatever you multiply. But 1 will now go to L minus 1. Anything, a fraction, suppose if it is 0.9, that will be 0.9 times L minus 1. Of course, you will take a, you will round off that value when this is a non-integer value, you will round it off to the nearest value. So is this intuitive enough for you, and is this clear on what histogram stretching does? All we are doing with intensity, not with frequency. Yeah, one more point here. One more good point here. See, this mapping, to find out this mapping, you need not have to actually do this calculation for every pixel. Suppose I have the 100, I have a 1000 by 1000 image. Okay, let me, since the space is full, let me write here. Assume that I have a 1000 by 1000 image, pixels image. So I have totally, how many pixels are there? 10 lakh pixels are there for me. On the other hand, assume that I have only I am using 8 bits. Okay, or maybe this, let me call it as B, number of bits I am using. For bits I could also, this is referred to as BPP. BPP means, what could have been BPP perhaps?
Bits per pixel.
Right, bits per pixel I am using 8. So can you now tell me what is L value here with 8 BPP? What is the L value here?
2 to the power 8 minus 1.
Right. No, L value. What is L is number of distinct values. What is
The
it?
power of 8.
Correct. Right. Maximum value you could store is the first answer you told. So this is equal to 256. Now this would have any value between 0 to 255. Now, here is another question to you. This way, if I keep going through each pixel and do this calculation, you could notice that I have to, let's say, do 1 million subtractions, 1 million divisions, and 1 million multiplications. Okay. So my calculations are order of 10 power 6 multiplications, subtractions, and divisions. Can you tell me a better way of doing it? Yes, please.
So we already know how many times a pixel is occurring. So like we only have 255 distinct pixel values.
You mean how many times a pixel is occurring, or a particular intensity is occurring?
I mean, particular intensity is occurring.
Okay, right.
Yeah, and just replace them with the new G value. Just replace those values with the new G value.
New G value. Yes, you are almost there. Very good. That's the right answer. Just the way you are doing, I think presenting it, I think there is still you could improve there. Can you tell it how you implement it now? Okay, you are right. In fact, your intuition is correct. The clue is here. There are 1 million pixel intensities are there, but there are only 256 unique pixel intensities. There are, if you have a image of 1 million pixels, there are indeed 1 million pixel intensity. At each pixel you have one intensity, but there are only 256 unique intensities. So this can take only 256 possible values are there for it. So can you leverage from that? That's the basic question.
So
So
we'll
now,
have to make a map, sir, or an index first.
it. Excellent. Very good. That's all you have to do. You just first go through each image from, of course, you don't even have to go through each image. If you have from fmin to fmax, you simply can make a map there. But for a simplicity, what you could do is you create an array, or not even array is required. After all, it is 255 values. Okay. So how do I implement? See, almost every time you should start thinking. Now it's high time, any subject, anything given, you should also think in how can I effectively translate it in while I am writing a program for doing it. Okay. So let's say you take here MATLAB is what you are using, for example. So your thing, you would start from 1, 2, 3, 4, 256. These are the indices of your thing. Or maybe to keep things simple, you keep 0 also here. Okay, indexing would start anyway from 1. Okay, but your intensities could start, your intensities could be from 0, but your indexing, if you are using MATLAB, could start from 1. So what I could do is I create some mapping. Let me that mapping not to compute with the new intensity. Let me call it as M for the time being. M of I equal to an index I. What would I do that? Suppose for a intensity of, if my intensity is I, all I need to do is I minus F min by F min minus F max into L minus 1. For a given I could do that. Okay. Suppose this can have 0 to L minus 1. So I would write something like this. M of I plus 1 is equal to, okay, I minus F min by F max minus F min into L minus 1. As simple as that. Look at now. Suppose I want to have for a 0, what is this? All I have to do is M of 0 will be there at M of I value is 0. So it will automatically look at M of 1. And for 0, I am calculating here. If you do not immediately get it, once I put, you just make a note of the what I have written there, look back there, then you will realize how simply you could write the programming part of it. And now every time all you have to do is g of, so you want to create g of x comma y. Okay, say for example, g of x comma y will be simply now equal to f of x comma y will give you the intensity, right? And for that, you just add 1, and there you look at in the new index for your map. Don't write a little more meaningful names. Let's say map or something like that. Map of f of xy plus 1. As simple as that. Okay. It is great if you get it immediately what I have written there, or else you just make a note of that. Think about it first. Don't worry to understand what I have written. Rather, you try in your own way a small pseudo code for this. Okay, then look at what I have written. Okay, maybe might have committed some mistake also, but hopefully not. No, if anybody sees a mistake there, point out then. Even now, if you see any mistake, hopefully at least did any of you get what I have written there for translating it into a code? So these are enough clues are here. Anyway, video also will be uploaded there. I want you to think about it, and if you still don't get this, I'll tell you in the next class. Everything is there. It's just that you need to see yourself. Okay. And again, there is an assignment for either image processing lab guys on histogram equalization. So this is what I would expect them to do also in similar lines. Any questions before I move to another very important topic? This is anyway histogram, the same formula there, 8 bits, it is 0 to 255. That will be the one. This is one example. This is the chest x-ray. Now x-rays won't be that bad unless the settings used by the one taking the radiograph put them so badly. Okay, this was purposefully taken a bad x-ray scan. So this is how it is. You apply it, you can see these bones of the chest x-ray and within the lungs, and a part of the heart also much better here. Okay, so now I would like you to take you through another important one. which you may perhaps have occasions, while particularly when you are dealing with images, you want to do this pre-processing and giving that as those images as an input to your CNNs or whatever you use would give you better results. So one of you were asking, is contrast stretching and histogram stretching same thing? Yes, they are the same things. Because you are doing this contrast stretching simply, as I said, 0 to 2, you know, Fmin and Fmax there. And of course, even without explicitly drawing the histogram also, you can do it simply looking at what is the minimum and maximum value, then finding out this mapping of where each intensity is going. Each intensity you have, you just need to find out the mapping between R and S. You call the input is R and output is S. All that it is doing is, for example, you initially might be having just this limit. Now what it will do, this for example, F min, F max, and then let's say L minus 1, all it is doing now is this line it is giving you. The F min is getting mapped to 0, F max is going to L minus 1. That's all if you want to draw like this. So if you ask me the question, is it mandatory to draw a histogram? Not necessary. But if you look at the histogram of the input image with the R and output image with the mapped R, each getting mapped to S, of course, that you see there histogram matching. So you could look at it in both ways. Hope that answers the question from one of the students. It's good, right? So let me now come here. See, we have seen now so far contrast stretching. What is this doing? So why we are doing this? Because we are assuming that your image is a good image if your intensities are spread in between 0 to L minus 1. All intensity are evenly. If you have something like this, if you instead have this, for example, here, okay, something like this, you are spacing also you are changing, and then you are bringing them to 0 to L minus 1. But you are not really looking into how many values, how many pixels. Suppose what could happen there is, yeah, you are not taking into account the count of pixels. So let me first give you, or at least try to give you, an intuition for histogram equalization. And then I will do all the, okay, before I do the formal derivations and all, let me try to give you the intuition for it. So please pay your full attention here. Otherwise, later you may find it difficult. Let us also say, for example, what I would essentially would like to achieve here is 0 to L minus 1 are there, intensities are there for my histogram. Let's say if I count number of pixels having 0, 1, 2, 3, so on and so forth, by the time, let's say I reach here, let's say 20% of L minus 1, I reached here, let's say 20% of L minus 1. By the time the histogram equalization would like to have 20% of pixels covered. What do I mean by that? For example, don't worry about what is this L value is. Okay, or L minus 1, let me, for a simplicity, let me put it as 100. Okay, L minus 1 is 100. Then 20% of L minus 1 is how much? 0.2 times 100. How much is that? 20, yeah? Right, 20, 100. 120% means it is 20%. So that should be obviously 20. So by the time I reach here a pixel intensity 20, if I sum, okay, by the way, Are you clear that suppose I give you a histogram, can you convert it into a probability density function? This I want you to answer first. I give you an histogram. Okay. I give you a histogram. I want you to create from that a probability density function. I want you to transform it into a probability density function. How will you do that?
Every value we can divide it by total number of pixels.
That's all. Very good. See, suppose if I have 100 by 100 image, okay, that means I have 10,000 pixels. Right? Now, suppose it might be out of 10,000, this might be having 100, this 200, 300, and so on. And if I divide all these values, simply my y-axis is nothing but I divide it by, so m by n image, let's say, you simply divide it by m by n. Each value of this bar here, okay, I divide it by m by n, then it will be a probability density function. What is the property of a probability density function you are obtaining through this process? What is the so when do you say, when can you accept something as a PDF here? So this, let me
Some will
give some
become
values also. R, PR of R. So when can you call PR of R as a probability density function?
when
Yes,
at
sir.
the L minus one it reaches one,
Hmm.
as in the sum will be one too.
Right. Can you just to say it in formula also, because later it will be useful for us? Summation of,
Uh,
I call this as R, I call this as PR of R. Now you tell me what should be the property to be satisfied here.
0 to RPR.
I equal to 0 to
R.
R.
PR
Hmm.
will be 1.
Is that so? No. Is this what you want me to write? No. Can you just correct it? Summation I varying from 0 to
L minus 1.
very good. And here what should I write? PR of
I.
very good is equal to 1. That's all. Then it will become your PDF. Okay. Is that clear? Any questions here? How you convert it? You can make a histogram into a PDF by simply dividing the values of your y-axis, which is the total number of pixels with that particular intensity, that is your y-axis, right? By the total number of pixels. That's all. That is going to get converted into a PDF. Now you could leverage profit from all the properties of PDF that has, if that is going to help you. Now, the question, I'll come back here. My objective is that by the time I reach here, say the maximum value out of that, if I reach by 20%, now I have here this, let me call this as R. What I am taking here is PR of R. Okay. Now I want to, so 20% of pixels. Okay. That means, let's say this, call it as, let's say R1. Okay. That's where I am getting it. PR of R. Okay. Should be equal to what I am saying now.
0.2.
It should be equal to
0.2.
correct. So that's 0.2. Here 20% I wanted there, or if this is 20 here in this case, I should get 0.2. Right. So how can you achieve this? Can you tell me any transformation? Let us now call the new variable as S of R, which from R, I want to apply a transformation S of R, that does something like this. So I will write something here. We will do all the derivation and all these things a little later, but before that, I want you to get an intuition for it. I equal to 0 to R, PR of I, okay? Rounding off and all, you forget about that for a moment. Can you tell me what this function is doing?
Sir, this function for the entire range of pixels that is still R, it is changing the intensity value to L minus 1.
Right. So maybe I'll add something here. See, there is R value. This is essentially, as I said, where should this R get mapped to? The new value is given by S here. So hope you remember I am drawing a little earlier. Suppose this is my F min, this is my F max, this is my R value, and of course this is my S value here. So this is how I am mapping in contrast stretching. Similarly, this probability density functions, probability PDF function values, till that R value, I am adding it up. Suppose, consider a special case here. Yes.
It's like think about cumulative
Yeah.
CDF
Correct,
only,
correct,
no, sir.
correct. That's right. So, suppose if your R equal to L minus 1, what would be this value when R equal to L minus 1?
1.
What is this
1.
value?
1.
1.
1.
Correct. Suppose, so what you are doing essentially here is make a note. Earlier, you are looking right away at what is the minimum value of R and maximum value of R. Now you are dealing with it in a different way. You are looking at how many pixels. So the moment you are here, 50% of pixels are there covered by this. Then what would you get here? This result. Suppose this is you reached by the time you for this particular
0.5.
value of R, you reached here 50%. So what will be this value?
0.5.
That's right. So what is the new value that you are assigning to that particular value of R now? L minus
Half
1
of
by 2.
255.
Correct, 255 by 2. This is what this function is doing. Of course, when your R equal to 0, it will look at 0 how many values are there. For example, of course, if it is there at 10% values are there, it will then move it to 0.1 times of L minus 1, of course. So if you, by the time for a particular value of R, okay, if 50% of pixels are there with that and values before that, you would assign it a new intensity of L minus 1 by 2. If it is 75% of pixels are there, you will give it as 0.75 times L minus 1. If 25% of there, you will give L minus 1 by 4. That is where your new S value will be. Now, earlier you could do this contrast stretching interpretation you could have done even without histogram. But this is where you could see we are clearly leveraging from the histogram here. And that's why you are equalizing. This is a one way of equalization that you are doing, not based on just the intensity values, but based on number of pixels that are having that particular intensity value or proportion of pixels that are having intensities less than that or that particular value. So which is giving us S of R equal to, you are varying I, let's say from for a R, you are doing it till R you are going. All the probability density functions you are doing it. Of course, this maximum value of this is 1. When this is 1, you want to map it to L minus 1. Else you want to map it to, otherwise it would be between 0 to 1 and only. Percentage it will give you finally, or proportion of values it will give, you multiply it. This is, of course, then you would also be doing round off of this value. Okay, so a round off, how would you do? Let's say you could add a round off to the nearest integer. I want to do it. How can you do that? To look it somewhat as if a lot of math is involved. If you want to write it, what you can do here is add 0.5 and take seal value of it. This expression has to be crystal clear to you. Does anyone have any doubts about this? We will now we are going to do all math associated with it, but unless you get an intuition for it, the rest looks very dry. Is this clear?
So, sir, this histogram equalization gives better output, sir, compared to the contrast stretching.
Well, that is our assumption here, and which many a time could be true. This is how, see, first of all, there is, if you ask, is it 100% guaranteed? I would say no. Our hope is we are coming up with a definition for what a good image means. How would be the intensities of that image? This is what we are making a hypothesis. The hypothesis of contrast stretching is that you can call an image as a good image. Okay, good image in the sense either visually it is you are able to make a good interpretation, or with this property, when you feed this to your algorithm, it gives you better results. Okay, that's what we are defining as good image. What makes an image good image? Here we come up with a hypothesis here that if my intensities are there from 0 to L minus 1, if I'm leveraging all intensities, it is a good image. That is the definition. That is the hypothesis that we have come up with for an image to be a good image. Now, when it comes to histogram equalization, the definition of what we consider as a good image, or rather than calling it as a definition, the hypothesis is a more appropriate word. We come up with a hypothesis that, well, you also look at how many pixels have that particular intensity. Don't just get carried away by the definition of fmin and fmax, because in your histogram, if you look at it, it might be the whole histogram might be there. Okay, just there is one pixel here, or one to few very small fraction of pixels are here. Then even if a single pixel is having zero intensity, this will not get stretched here, it will remain same. But after all, just 1 or 2 pixels are having this intensity. So rather than just looking at minimum and maximum, why not I see the proportion of total pixels and accordingly distribute my histogram? That's the idea of histogram equalization. What you asked is a very important question. So I hope the explanation is answering your question, or is there any doubt there?
Okay, sir.
So many a time you cannot blindly apply this any of this contrast stretching or histogram equalization, these methods blindly. You need to look at the image intuitively. You should get some understanding, and that should make sense to you. You should also be looking at the images and see whether is this making sense. First of all, that should enhance that should be enhancing the image. When you look at, you should feel that, otherwise there is something going wrong. So none of these methods are always guaranteed to improve the image quality when you apply it. But nevertheless, there will be good number of instances, particularly when you see that contrast. See, what is of interest to you is just a part of your whole image, assume that, and then you have cropped your image to a small region. What could have happened is there might be a high contrast objects in the rest of the image. Because of that, the image, after all, you have, if you are using 8 bits, you have only 0 to 255 range. But from the entire image, you have cropped and you have taken a particular portion only. Assume that other portions have a bright part. So this obviously, then you might be having, let's say, from 0 to 100 only. But When you are just cropped this and took this part, what would be better is you do a better histogram equalization in such cases. Even simple contrast stretching also would definitely improve your results. If that is not the case, so it is a context dependent. If the scenario, you could come up with a counter scenario, a scenario which is opposite to it, where histogram equalization could perhaps be not the right thing to do. But there are, nevertheless, there are quite a few scenarios and contexts and applications where this could definitely improve your results. You have assume that you have an MR image or any other, even normal image taken with a camera. There are bright objects in that. Since this scaling is between 0 to 255 there, when you crop and took only portion of that, this will help you. It need not be always this case. Suppose you have taken that under a low light condition. You have seen a couple of images where gamma transformation has made sense. Same thing happens with this also. This is also another alternative where you could improve the contrast here. Is that clear? Those are all important points that you raised. So I just spent some time on it and hope it gave you some idea on when it could be useful and when it might not be useful. Is that clear to everyone? Okay. So then let me now go through the formal derivation of this that would now highlight the important properties of this histogram equalization. So we have written now S of R is equal to, you applied some transformation on R. Okay. What is the transformation? That's what we were figuring out. So the way we apply transformation, so well, before that you could see now there are two variables S and R. Tell me now, here I have a probability density function R. Will the result of this applying this transformation will still give me a probability density function? Suppose what I got there is PS of S. Will I still get a probability density function there now or not?
Yes, sir.
Yes, that's right. So you have a variable R, you applied a transformation to it, the corresponding probability density function is R, probability of R. You transform to S by applying a transformation, and you still have another probability density function, which I call it now as PS of S. I'm using a different subscript here. Reason being, these two probability density functions could be different, because now the probability density function is written such a way that by the time you reach 50% of your pixels having that or intensities below that, it should be somewhere in between. So that probability density function, obviously you are doing it for achieving a particular type of probability density function. Okay. Now in calculus, while you are doing it, maybe if you are doing a course related to calculus, you would have studied that if this whole transformation satisfies a quality of monotonically increasing function, monotonically, this transformation is equivalent to a monotonically increasing function. What does that mean? Suppose I have R here. Let us not become too technical, but rather let's try to get an intuition of what it is. R and S, assume that. Okay. So this, for each R, I got an S. Assume that I got this one. When do I call something as monotonically increasing is with the increasing value of R, S also should either increase or remain same. Okay, suppose I have a function like this. This is not monotonically increasing. On the other hand, if my R and S is like this something. Okay, so it is never decreasing with R. So let me put it in the perspective of intensities. Here, you consider an intensity of I1 and I2. If I1 is greater than or greater than I2, what is guaranteed is this is getting mapped to something here. This new intensity is getting mapped to something here. So let's call this as I1 prime, I2 prime. What is guaranteed is I1 prime is greater than or equal to I2 prime. This is called as monotonically increasing function. Whenever you are applying any transformation on intensities, this should be respected or this should be satisfied, because if relatively one pixel is brighter than the other pixel, even after applying the transformation, that relative relationship should never get disturbed. Of course, what should happen is if it is strictly monotonical, then what should happen is I1 prime also should be greater than I2 prime. Is the interpretation we are doing is clear? If your sorry, one of you has right, what I have written is actually less than. So either yeah, let me put it as less than, then it should be less than or equal to here. Thanks for pointing it out. Correct. So if I could have written opposite also, if I have written the I1 as I2 and I2 as I1, but here for the values I have shown here, if you were, yeah, let me otherwise write it as I2, this as I1, this as I2 prime, this as I1 prime. Then all my earlier statements hold good. Okay, good. That's a good point. Is this clear? Are any questions here on first understanding the important point that your function should be a monoton, the transformation that you are going to apply should be a monotonically increasing function. Ideally, it is good if that function is strictly monotonically increasing, but nevertheless, it is fine that even if your function is monotonically increasing. Well, in the interest of time, I need to break here. So I'll continue the derivation part for this equation, and also looking at what would be under this condition if I apply. So you yourself think about it. Hope you have noticed one thing here. We are gradually moving into a continuous case here. Okay, we deal with a continuous distribution just to see how what will be the properties of that we obtain as a result of applying this transformation. Okay, then anyway that will help us to make some interpretations about PS of S, whether is it having the desirable property or not. Anyway, that should have been clear intuitively, at least for now, from this expression. We will continue our analysis of the histogram equalization in the next class.